So let's jump right in. We've got this global puzzle on our hands. All over the planet, communities are dealing with major water problems. But here's the weird part, the thing that makes it a puzzle. One town's wells are bone dry, while just a few states over, rivers are bursting their banks. I mean, how can so many places be in a water crisis, but in completely opposite ways?
And that's the big question, right? Are all these things, the droughts, the floods, the shortages, are they actually connected? Are they all just different clues in the same giant mystery? Well, to figure it out, we've got to play detective and follow the evidence.
And look, we're not talking about some abstract idea. These are real problems for real people. You've got places literally running out of water. Take Porterville, California. Their wells are just dry. Over in Yakima, Washington, farmers are desperate for water they used to count on from snowmelt. And for the Navajo Nation, their most vital water sources are just dwindling. But then you flip the coin, and you have the exact opposite problem, way too much water. Vicksburg, Mississippi, rivers are overflowing. Boston, the city streets are flooding like never before. It just doesn't seem to add up. What is going on?
Okay, to crack this case, we have to step back and look at the whole crime scene, so to speak. We can't get bogged down looking at just one dry well or one flooded river. We've got to see the bigger picture, the whole massive interconnected system that's shuffling water all around our planet. So let's get our investigation board up and see how it all works. All right, think of this model as our master key. It shows us that all the water on Earth isn't just sitting in separate buckets. Nope, it's all part of one giant connected system. You've got water moving from the air, down to the ground, and even deep, deep underground. It's always on the move, always changing. And figuring out how those pieces connect, that's going to be the key to solving this whole thing. So where do we start our investigation? We're heading to the coldest parts of the planet. Why? Because that's where a massive amount of our fresh water is locked away in ice and snow. Let's see what clues scientists have dug up from these frozen landscapes. Wow, okay, this picture really says it all, doesn't it? Just look. On the left, you've got this photo from 1917 of a huge glacier in Alaska, just jam-packed with ice. Now look at the right. Same spot, but in 2005. The glacier, it's just gone, replaced by a field. I mean, that's not just a small change. That is a total transformation. It's kind of shocking to see side by side. And this isn't just a one-off thing with that one glacier. Scientists have the data, and it's a global trend. Glaciers everywhere are getting smaller. The snowpack that builds up in the mountains every winter, there's less of it. And what little snow there is, it's melting way earlier in the year. Now, why does that matter? Well, it's absolutely crucial for communities like Yakima, Washington. The farmers there have built their entire lives around that slow, steady trickle of meltwater to get them through the summer. But when you have less snow, and it all melts in a rush in the spring, they're left high and dry when their crops need it most. So it's pretty simple, right? All that melting ice has to go somewhere. So for the next step in our investigation, we're going to follow the water. Let's trace its path as it flows down from the mountains and into our rivers, our oceans, and even way down, deep underground. Okay, so first stop, the ocean. A ton of that meltwater from the glaciers is pouring right into it. But there's a double whammy here. See, water also expands when it gets warmer. So you've got more water coming in, and the water that's already there is taking up more space. The result? Something we call sea level rise. It's just a slow, steady climb in the average level of the ocean. And you might be thinking, a little rise, so what? Well, for a coastal city like Boston, it's a huge deal. Even a few inches means that regular old high tides can now creep much further into the city. Storms become way more damaging. It's the reason a city that's been around for hundreds of years is suddenly getting these weird, sunny day floods right in its streets. All right, let's head back inland and look at our rivers, because this is where things get really wild. These changes in snow and rain are creating two totally opposite problems. On one hand, you've got a place like Vicksburg, Mississippi. The snow is melting super early, right when the heavy spring rains hit. It's too much, too fast. The river system gets overwhelmed, and boom, you've got floods. But then, in other places like the Navajo Nation, it's the opposite story. Less snow, less rain. The rivers they've relied on for centuries are literally just drying up. And then there's the hidden part of the system, the water we can't even see. It's the groundwater, stored in these huge underground pockets called aquifers. For a dry place like Porterville, California, this is their lifeline. But you gotta think of these aquifers like a bank account. Rain is the deposit that keeps it full. But right now, with less rain, the deposits have basically stopped. People, though, they keep making withdrawals, pumping water for their homes, for their farms. And we all know what happens when you keep taking money out and don't put any in. Eventually, the account is empty. The wells run dry. Okay, let's pause and recap. We've collected all our clues. We've got shrinking glaciers, rising seas, we've got rivers that are either flooding or vanishing, and groundwater that's disappearing. They all feel like totally different problems, right? But what if they're not? What's the one thing that connects them all?
Yeah, what's the common thread here? What's the single culprit behind every single one of these huge changes to our water system? The answer is actually surprisingly simple. It's not some big, dramatic, sudden event. It's just one small, steady change that's been quietly happening in the background. This is it, the smoking gun. A rise of about 1 degree Celsius in the planet's average temperature. I know what you're thinking. 1 degree, that's it. It sounds like nothing, right? But here's the thing. In a system as finely tuned and complex as our planet's climate, a tiny, constant push like that is enough to kick off a massive chain reaction. So now it's time for the big reveal. Let's connect all those dots. We're going to see exactly how that one tiny number is responsible for all those huge and hugely different problems we've been looking at. And this, right here, is the absolute core of it. This is the main takeaway. A tiny change in temperature in the atmosphere is causing massive, system-wide changes to water on Earth. It's the first domino. It's the single trigger for everything else we've been investigating. And this chart just lays it all out plain and simple. That little bit of extra heat means less snowpack and an earlier melt. The impact? Water shortages in Yakima. That same heat changes rain patterns so groundwater doesn't get refilled. The impact? Dry wells in Porterville. The heat melts ice and expands the ocean. Impact? More floods in Boston. It messes with the timing of everything, causing crazy river flows. Impact? Floods in Vicksburg. You see? It all traces back to the same source. It's all connected. So let's go back to our investigation board one last time, now that we've cracked the case. It all starts with that 1 degree of warming. That extra heat pulls more water up into the air. It messes with where and when that water falls back down, and it melts the ice and snow that's been stored for centuries. That single, simple change kicks off this incredible cascade of effects. And that is how we solve the puzzle. It's why so many different communities are having such different, yet deeply connected water problems. When you step back, it's a pretty powerful idea, isn't it? The dry wells, the flooded streets, the disappearing rivers, they aren't random, isolated problems. They're all symptoms, all part of one big, interconnected story about a system reacting to a single, small change. And that, of course, leaves us with a really big question. If just 1 degree can do all of this, what happens next?